A CVE has been found in the Linux kernel, and not just any CVE, it's a CVE in Rust code. Linux kernel Rust code sees its first CVE vulnerability. Really interesting stuff going on here, guys. It has to do with a line of unsafe code in a Rust driver that made its way into the Linux kernel. Let's talk about it. So the driver we're talking about today is this thing that's known as Android Binder. So Android Binder is basically an IPC, an inter-process communication mechanism within Android. Basically, instead of talking through like some really kind of dirty syscall interface, you can use Binder to do IPC to send messages through message queues and allow app A and app B to talk to each other cleanly through some kind of kernel mediation, right? And so recently there has been a rewrite of the Rust Binder service in Rust, and it's made its way to the Linux kernel, but a race condition was found in the Rust implementation, which is actually crazy because like the whole point of Rust, mind you, is to prevent things like buffer overflows, memory corruption, etc. But we have a race condition in Rust, which is pretty crazy. Obviously, guys, to get to a place where we have race conditions in Rust, we have to be using the unsafe tag, and unfortunately, we do use the unsafe tag. And this unsafe tag basically disables a borrow checker for the code inside of that block, and as a result, you get the ability for race conditions and other issues to occur in the code. They have this ability to track nodes, right, in a doubly linked list. Also, unrelated, guys, I'm at 981,000 subs. I'm almost at 1 million. If you like any of this stuff, just do me a favor, hit that sub button. It's really easy. It's just press it. It's free. A doubly linked list is a very simple data structure where you have the head, like the pointer to the first element in the list, and then that node has a previous pointer that points back, an A, like some element inside of that list, and then a next pointer that points to the rest of them, and that can go on forever and ever and ever. And so inside of the driver, they have this way to track node deaths, which means I'm assuming like a piece of memory that has been allocated that needs to be released back into the wild, and they track it as this death element. And this is tracked as a doubly linked list. Now you'll notice there is an unsafe tag on node inner death list remove of self. So the way that they remove an element from the doubly linked list is unsafe, which I guess makes sense. This operation is unsafe because when touching the prev next pointers of a list element, we have to ensure that no other thread is also touching them in parallel. Now, what they say here, and typically if you see unsafe code in unsafe Rust in a code base, you're supposed to specify with a comment why the unsafe block is okay. You call it a safety comment, because unfortunately, guys, in a system like the kernel or doing like embedded systems, Rust is going to have unsafe code. It's just kind of the nature of how you have to get the system to interact with other parts of the system. Like if you make a piece of Rust code, for example, that interacts with C code, that FFI, that foreign function interface, is naturally unsafe. So you will see unsafe code in Rust. But you also specify what the safety implications are, right? Like why is this piece of unsafe code supposed to be allowed, right? Well, a node death is never inserted into a death list of any other node than its owner. So it is either in this death list or a node death list at all. And the reason this is okay is before they go over the death list and remove the node from it, they get a lock on that list, right? So if you have this thing here in a multi-threaded scenario, what gets very dangerous is if multiple people can do operations on that list at the same time, right? When you're doing an insertion or removal from a doubly linked list, you are temporarily storing state about the node to remove it from the list. So what you would do, for example, to remove B is you would say that A.next equals B.next, and then C.prev equals B.prev. But those two operations together are not atomic. They're happening separately. So if two threads can do that same operation on a list at the same time, you have a race condition in who completes first. And if you interleave those instructions, you're going to have a bad time, right? You're going to lead to metadata corruption about the linked list and as well as the heap that uses a linked list, right? So in a scenario where you want to remove a node from a doubly linked list, you have the list itself and the node you want to remove from it. List has like a head element, right? So what you do is you say, okay, I'm currently at node N. I want to get the previous item and the next item, call them P and Q. If P exists, meaning you have an item behind you, you just say the item behind you's next is a thing ahead of you, right? So you basically remove yourself from the list. Otherwise, if you have nothing behind you, you are the head of the list, so you say the list head is now equal to the thing ahead of you, right? But the issue is, imagine in a multi-threaded environment where this is going to happen 2 times, potentially at different locations in space, right? Or in different times. What you eventually get is, let's say, for example, this function got ran inside right here. So you have the kernel is running thread A, there's a context switch, and now thread B runs. You're gonna start running all this again with a linked list that has only been half removed, right? So you're starting to update pointers in wrong ways. You're pointing one of the nodes to freed memory, and you're pointing one of the nodes potentially to a corrupted value. It just gets really messy really quick. And so an assumption they had is that because the death list, the list of node deaths, never existed in two locations at once, this was not a big deal. We were okay to have this be unsafe, right? Well, here is the fundamental problem, okay? What happens is they take a lock of the list, but then they move all the items to the local list on the stack and then drop the lock. Because of this, there are two locations where the list exists, and both locations think they have exclusive ownership of that data structure, but the pointers in that list both point to the same location. Because of this, you're able to have two separate threads that use the unsafe removal method, and they both have different copies of the same list doing the same operation. You're able to do this and interleave those next improve update instructions and get crashes in the kernel. Like crazy stuff. You see here, basically this bug is them trying to access this memory address, which is an address between user and kernel address ranges. Basically, it's not mapped as a PFN in the kernel. And you can see here that it's derived from likely some instruction in the update or removal of a index pointer or a prev pointer. So this is CAC 706 and they have CAC 70E. So maybe it's like, you know, they have the node structure and then the node structure plus 4 is going to be the address of the next pointer, for example. It's not 4, it's like 5, but you see what I'm saying. And again, the whole reason this is possible, by the way, is because, you know, they have a check that says that this list can't exist in two locations, but the problem is they take the list, move a local copy onto the stack, and don't have a lock that locks up both the one that's real and the copy. So because of this, two separate threads can access the list at the same time by just triggering a removal again, right? And so the way that they fix this is kind of neat. They basically, instead of like doing a core mem take, they just iterate over the list. So again, if you're not a Rust person, basically the death is an option. So it's either gonna be some option or it's gonna be some death or none. And they iterate over that list and then get an exclusive lock on that inner list and then do something afterwards, right? So they'll remove it after they call this. Basically, they're getting rid of the fact that there is a local copy on the stack called death list, and they're not iterating it over like this. So they basically went from doing a boomer loop sort of to an actual like while let sum, which is a proper Rust thing to do. Also, I want to make sure that I'm like being very clear here. This is not me like shitting on the code base. Like doing this in Rust in the kernel correctly is like very hard to do. So this is more, I want to make sure I'm talking about the bug as it is, and I'm not like being like, oh, rah, rah, rah. Like I couldn't have done this. I think you couldn't have done this. Maybe you could have. I don't know. Go work for the Linux kernel. Go figure it out. Go do it. But yeah, anyway guys, that's it for now. Thanks for watching. I appreciate it. If you like this video, hit that sub button. I do sincerely appreciate it. And then go check out this other video about a different bug that you might also like, or this other video about how to do a buffer overflow attack. It's pretty neat. See you there. Goodbye.